Greetings and welcome back to Mathamopoulos. Now in this episode we're going to be continuing the Applications of Calculus series, and today we're going to be looking at the disk method. So what's cool about the disk method is that this is actually a pretty decent application of calculus to the real world. This is commonly used in multiple forms of manufacturing and engineering. When you rotate a two-dimensional area around a line, it creates a 3D solid, or just simply an abomination. So the disk method is a way of finding the volume of a rotational solid, or a rotational abomination. We're able to calculate precise volumes by cutting the shape into infinitely thin slices perpendicular to the axis of revolution. What the disk method really does is find the area of each infinitely thin slice, and then by integrating it, it adds up all those areas along the length of the solid, which gives us a precise volume. Now, the equation used for the disk method is based off of the area formula for a circle, the antiderivative from a to b of pi times r squared, where r is a function in terms of x that represents our radius, and the thickness of each disk is represented by dvex. The thickness in this case is dx because you have to integrate with respect to the axis that you're rotating around. So let's try an example. Find the volume formed by rotating the region bounded by the parabola y equals 4 minus x squared and the x-axis about the x-axis. So let's just draw a picture of what that might look like real quick. And so how I would start this problem would be to find the bounds of our antiderivative. So we're just going to set our function equal to 0 and solve for x. Now we're going to plug those x values into our equation, and looking back at the equation, we have big R. Now remember that we called big R a function in terms of x that represented the radius. So we need to remember that the distance to the function from the x-axis is the function. What do I mean by this? Well, the distance from the x-axis to the function, it would be our radius. So in simpler terms, the radius of the function at x is just the value of the function at x. So in this instance, big R is just the function. So we're going to plug in our function to big R and simplify the equation a little bit. We can pull out the pi because the pi is constant, of course. And if we plug that into our calculator, we should get an answer of 512 over 15 pi. Here's another example. Find the volume of the solid formed by rotating y equals the square root of 16 minus x squared about the y-axis. Now, I'll let you guys give this one a shot.
Idiot alert. Idiot alert. Idiot alert.
What?
Idiot alert.
What's that sound?
Idiot alert.
It's the idiot alarm!
Alert.
Oh no. Did you even listen to the video, you dumb asymptote?
Haha, math pun, I liked that one.
The slices have to be perpendicular to the y-axis, dude. The radius is the distance from the y-axis to the function in this problem. You have to integrate with respect to the axis of rotation, meaning the bounds have to be the intersection points on the y-axis, and you have to solve this equation in terms of y. That's it. Let's just do the problem together. The first thing we have to do is rewrite the function in terms of y. Then that will allow us to find our bounds, the y-intercepts. And then we can plug all of that into our equation and integrate with respect to y, of course, to get 256 over 3 pi. Now let's just do one more problem. This problem is similar to the first one we did, but instead of rotating the function around the x-axis, we're rotating it around a line that's parallel to the x-axis. So let's find the volume of a solid formed by rotating f of x equals 2 minus x squared about the line g of x equals 1. And again, let's immediately note, g of x equals 1 is parallel to the x-axis. Therefore, this entire problem is going to be with respect to x, lest we make another mistake like that last problem. First, we should find our bounds. Now note that the bounds aren't going to be the x-intercepts. They're actually going to be where the two functions touch each other. So we're just going to set the two functions equal to each other and solve for x, which gives us x equals plus and minus 1. Now to find big R, we need to do some top minus bottom action, similar to our last video, because when rotating around an axis that isn't the x or y axis, the radius is either going to be bigger or smaller than the function. Technically, this whole time, we have been doing top minus bottom, but because the bottom function was the x-axis, y equals 0, we were subtracting 0 from the function the whole time. And I just didn't bother writing it, not because I forgot to mention this point or anything. And if this were spinning around an axis parallel to the y-axis, you would do right minus left instead. Or you could twist your neck to change the perspective of the graphs to become top minus bottom, like I used to do, and get weird looks from your math teacher. So by doing top minus bottom, we end up figuring out that big R equals 1 minus x squared. And now we have all the information to just plug and chug. So plugging in everything to our equation, we should end up getting a volume of 16 over 15 pi. I hope you enjoyed today's lesson, and I hope you come back for the next episode where we will cover the washer method. That's it for this episode of Mathamopoulos, and thank you for watching. I hope you enjoyed today's lesson, and I hope you come back again for the next part. Where we'll be